Okay, we're now ready to talk about the fundamental building block for the whole course, which is sinusoids. So just to remind ourselves, let's look at what the sine function and the cosine function are. So let's look first at f of t is equal to sine of t, and we'll look on the interval, we'll just say 0 to 2 pi for now. Okay, so let's look at that. So what I'll do is I'll use linspace to generate maybe 100 samples between 0 and 2 pi. And I will just go ahead and plot t sine t. And I'm going to be using radians here, by the way. So this is, yeah, you could think about the sine as being a function of the right triangle and looking at the angle in degrees, but I'm going to use radians in this course. Okay. So we'll say the x label is t in radians. Okay. So, whoops, got to run this block first and import all my stuff. Now I can run this block. Okay. So there's the sine. So the sine starts at 0, goes up to 1 a quarter of the way through, goes back down to 0 halfway through, down at -1 3/4 of the way, and then back at 0 where it started. So I could go back to the right triangle and derive all this geometrically, but really for this class I want you just to understand that sine is something that has this pattern. It lives over the interval 0 to 2 pi, and it goes up, down, and then back to where it started. Okay. Now what about cosine? Let's look at that as well. So, and let me actually add a legend here so that we can look and see which label both these. So to do a legend in Matplotlib, it actually takes an array of strings. Each string corresponds to the plots in the order that they were created. So the first one I'll say is sine of t. And then the second one is cosine of t. And by the way, one kind of cool thing you can do with these legends and titles even and axis labels is you can use LaTeX, for those of you who've seen that. So anything enclosed in these dollar signs here would be interpreted as LaTeX. Okay, so I see sine is in blue, cosine is in orange. So cosine is just sine shifted to the left by a quarter of its cycle. Or, you could say sine is cosine shifted to the right by a quarter of its cycle. So cosine starts at 1, goes down to -1, and comes back up to 1. And if I made these, if I made the domain longer, then what we'd see is that these repeat themselves. So we say they're periodic. And remember what we said about things that were periodic on Friday. If we go to listen to them, we should hear them and perceive them as a pitch. So let's go ahead and do that. I'll put on my headphones so I can hear. So let me say, okay, let's say I got a sample rate of 44,100. I'll say maybe just make a second of audio. So I'm taking that many samples. And okay, now let me, actually I need to introduce one more formula. So let me actually write another version of this that's a little more general. So let me introduce what I call a sinusoid, not just a cosine or a sine, but kind of a more general thing. So say that is f of t is equal to a times, big A times cosine of 2 pi f t plus phi. Okay, so here's the formula. And what we say is A is the amplitude, F is the frequency in hertz or cycles per second. T is the time that we're looking at. And then phi, or phi, is the phase. Okay, so let's mess with some of these parameters a little bit and listen to the results. So first of all, let's just make sure the units work out. So frequency is cycles per second. So we have cycles per second times time, which is seconds. And we notice that second up here cancels out with a second down here. And we're just left with cycles, okay? So if I look at a frequency of 1, for example, that's saying I should go through 1 cycle in a second. So if I plug in 1 second, I should have 2 pi, and I do. So 1 times 1 is 1, so I have 2 pi, okay? If I have a frequency of 2, then when I plug in 0.5, I should have only gone through 1 cycle. So actually, let me write this alternatively. There's something you can define called the period, which is 1 over the frequency. So an alternative formula for this is f of t is equal to a cosine of 2 pi t over t plus phi. Okay, there we go. So notice that, yeah, here's another way I can write it. I can say, or actually, let me rearrange this. But I like it better if it's written like this. Okay. So here's another way to think about it. 1 over the frequency is the period. So the higher the frequency gets, the more quickly this repeats itself, the smaller the period gets. So the period is the interval over which this repeats itself. So actually, before I even listen to it, let me just plot a couple examples. So let's say that I'll make A1, I'll make F2. I'll just sample T between 0 and 5, I guess. And yeah, let's just look at this formula. And yeah, I'll make phi 0 for now. So I'll say y is equal to np dot cosine, whoops, a times np dot cosine, 2 times pi times f times t. So here we're taking advantage of all this element y stuff, plus phi. And then I'll go ahead and plot it. All right, actually, let me take a little more samples than that. Maybe I'll take 1,000. Just so it comes out a little smoother. Okay, so I chose a frequency of 2. So you see it actually goes through 2 cycles every second. So these are units of seconds down here. If I make the frequency 3, then it'll go through 3 cycles per second. So see, the frequency is going up, the period goes down. The amplitude controls how the range of this sinusoid is. So I make the amplitude 2. Let me actually fix the y limits here. All right, so anyway, that's an amplitude of 2. If I go back to an amplitude of 1, you see it's not quite as big. So this corresponds to getting louder, actually, or quieter if the amplitude goes down. Phi is just a phase shift. So let me make that pi over 3, for example. So this will move it to the left by pi over 3. So see how it moved a little bit over to the left? That was starting off at 1 before, but now it's not. It's actually starting a little bit earlier over here. Okay, so this whole thing shifted to the left. So this formula can get us every single sinusoid that we care about. Okay, so let's enough chatter. Let's actually listen to this. I got my headphones on after all. Okay, so I'll use the same formula. I'll say, let me make my sample rate 44,100. Let me start off with a frequency of 440. And I'll just, amplitude will be 1 for now. Actually, it doesn't really matter what the amplitude is in Jupiter, because Jupiter automatically scales everything to take up the full range. And I'll just make phi 0. We're not really going to be able to hear the difference with just a single sinusoid. All right, so now let me do ipd.audio Y rate equals SR. And let's listen. Well, what did I do wrong here? Oh, I forgot to do my t. So t is equal to MP, let's say maybe 2 seconds. So sample rate times 2 over sample rate. So that will give me up to from 0 to 2 sampled in at that rate. Okay, so that's a very boring A, concert A, pure tone, 440 hertz. Let me just do 1 second is enough, I think. Let me go up to 660 hertz. Oops, need to rerun this. That's an E, so that's a fifth above A. Actually, let me put maybe 2 frequencies together. So I'll do, this is F1 times T plus F2 times T. And I'm not even using the phase, so let me just get rid of that now. Or the amplitude, I'll just make them both amplitude 1. So let's hear the 2 together. Okay, so the fifth above a note, it's called a fifth, sounds nice with that. And we'll talk a little bit more on Wednesday, I think, on why that is. Okay, so these are pure tones. You notice they sound a little more boring than the sawtooth wave that we made in class on Friday. Just to remind you, the sawtooth wave I would get by doing something like T is equal to MP dot A range SR, and then I would say Y is equal to T mod 100. That would get me very close. That would give me a period of 441 actually. Whereas this thing has a period of I'm sorry, that would give me a frequency of 441. This one has a frequency of 440, but very close. You probably won't be able to hear the difference. So let's listen. So they have the same pitch, but the pure tone doesn't have as much color, or it doesn't have that sort of grittiness to it. Okay, but these pure tones are the building blocks for every sound out there, it turns out. So we'll talk more and more about that as we go along. The last thing I want to show you is, well, okay, let me just first define a general formula for making musical notes. And we'll flesh this out more this week, but I want to give you the basics here. So, formula for frequency of musical notes. So as I said, 440 hertz is what we call concert A. That's what orchestras tune to. But in general, we have this formula that we can use for an equal tempered scale, called the equal tempered scale. So there are 12 half steps. So we have A sharp, B, C, do I know what comes next? C sharp, D sharp, E, F sharp, G sharp. Did I get all 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So that's one spelling of the 12 possible notes. What I'll say is I'm just going to put numbers to them because we're going to need to use numbers in Python. But I'll say that A is a 0, and then each one of these is a half step up from that. All right, and then actually this repeats itself. So then we have an octave above. This would be 12. A sharp, an octave above would be 13, and so on. So it actually circles around. So the formula is the frequency using these note numbers is equal to, so let me call this, I'll call this the note, and then I'll call this P for pitch number. And then frequency is what I'm computing here. So frequency is equal to 440 times 2 raised to the P over 12. Okay. So that's the formula. So let me just quickly write a method to do that, because that'll be much more convenient. So I'll say def get pure tone. I'll say, or maybe get note frequency P, and so I'll return 440 times 2 raised to the P over 12. All right. So let us go back and do something very similar to this and start listening to some different notes. So let me say the frequency is equal to get note frequency 0. So just make sure that's still an A, just make sure it's working. Okay, there's my concert A. Let me go ahead and actually just make a loop. I haven't talked about loops yet, but I'll talk about them more this week. But I can repeat this 10 times. Or maybe I'll do all the half steps. I guess it's not going to like that. I thought it would make different audio plots here, but it's not doing that. So instead, what I'll do is I'm going to get a little fancy here, but don't worry. So I'm going to put all the half steps next to each other. So I'm going to make an array that holds all the half steps together by using this function in Numpy called concatenate. Let's see. Okay, yeah, and let me make this a little shorter. So I guess I'll say maybe each one's a half of a second. Now remember, if I'm using arange expects an integer parameter. So if I want to have a half a second, I do sample rate over 2, but that's a float, as I told you before. So we need to cast it as an int. So this will be a half a second of audio for each half step. Whoops, I called this Y, not X. Okay, let's listen to that. Of course, I then have to call the method in the loop. I have to say for each one of these half steps, I need to get a new frequency. I'm going to call this P, just so it's consistent with the parameter name. Okay, so for every half step, starting at 0, so we call these half steps. Wow, they didn't line that up too well. Okay, anyway. So for every half step starting at 0, we go up. This is called the chromatic scale. Okay. And if we keep going, we'll hear that we circle around. It's the same note, but it's higher up. We call those octaves. Okay. So I'm going to have you do just a quick exercise where you make a square wave, and I'll just note that there's a useful function in Numpy called Sign. I don't want to say sign, but it's mp.sign. And what this does is if you feed it any number that's negative, it'll give you a -1. If you feed any number that's positive, it'll give you a +1. And so this is really useful. If you feed a cosine to this, then it'll turn it into something called a square wave. So I want you to make a square wave and then listen to what that sounds like.